Hey, good morning everybody. This is Mr. Ainsworth. We're going to get into section 4 here in pre-calculus and talk about all kinds of trigonometric identities and how to apply them. We'll do some proofs, we'll simplify some expressions, we'll learn how to use these formulas and identities. Before we do though, let's review what we did yesterday in the previous lesson. Alright, we're going to graph a couple functions here. The first one here is y equals negative sine of pi fourths times x minus 1 and then plus 3. I can see that the amplitude here is the absolute value of negative 1 or 1. The amplitude is 1, same as the original amplitude of the sine function. This negative sign right here is a reflection across the wave axis. So it's a reflection across the wave axis. Not the x-axis, but the wave axis here. We'll have to figure that out. This is b here. B is pi fourths. That means period is 2 pi divided by b, which is pi fourths. After you multiply by the reciprocal, the pi's cancel and you get 2 times 4, 8. So the period length is 8. And let me see if I subtract 3 on the other side. I get y minus 3. So, or you can just understand that that's k there. H is here. K is here. H is 1 because it's always x minus h. And then if you bring 3 on the other side, you get y minus k or y minus 3, where k is 3. So my shift is h comma k. So in this case, h is 1, k is 3, so 1 comma 3 for the sine curve. Okay, so now what we do is we go ahead and graph the wave axis. Wave axis here is y equals k. Alright, y equals k in general, or in this case, y equals 3. So I'm going to start by drawing the wave axis here at 3. Let me grab a horizontal line and make it easier for me. Okay, so there's my wave axis at y equals 3. My amplitude is 1 because the absolute negative 1 is 1, so it bounces above and below this. So if this is 3, this is 4. So no. It bounces in between these two dotted lines. Alright, there, that just helps me guide my function. So it oscillates and goes up and down between these two horizontal dotted lines given by the amplitude of 1. Question is, where does it start? Okay, so let's talk about that. Typical sine wave starts here at the origin. That's not translated, but this one's been translated 1 right, 3 up. So you got to go 1 right and 3 up. So 1 here, 3 here. So now my sine wave starts here. Okay, starts at 1 comma 3, and then it typically goes up and back down. Alright, but this is a reflection across that. So instead of going up and back down and then back up, it's going to go down and then up and back down. It's going to be the opposite of what normally occurs. Okay, so I'm going to start here, and where am I going to end? Well, I'm going to end 8 units to the right. So 1, 2, 3, 4, 5, 6, 7, 8. I'm going to end it right here. I'm going to graph one period only. Let me double check that. 2, 4, 6, 8. Yeah, good. Okay, and divide it up into 4 equal parts as I always do. So I'm going to start here and I'm going to end over here. Now typically I'd go up and then back down. Okay, and that's my typical sine wave, but I've got a negative here, which is a reflection across the wave axis. So I'm going to go down. So I go 1 to the right, or 1/4 to the right. Instead of going up, I'm going to go down. Back up to the wave axis, and then go 1/4 again to the right, and go up to the wave axis, and then back down. So I go down, and then back up, and then back up and down. So it's opposite of what normally occurs because that negative is a reflection across the wave axis. And that's one period only. Okay? This is the period length right from here to here. P equals 8. One period only. One period only. If you need to draw more, you could. You just repeat the pattern. Okay? And you could check that on your graphing calculator if you like. That's correct. Okay. On the second one, amplitude is 3, b is 4 pi, my h is negative 1, and k is negative 4. So let's write this down. So a is 3, b is 4 pi, p is equal to 2 pi divided by b, which is 4 pi, which is 1/2. Excuse me, I didn't say that correctly here. Did I do that right? So, yeah, okay. So 1/2 here. And then, let me see my shift. is going to be -1 comma -4. So -1 comma -4. My wave axis is y equals k, so y equals -4. Okay, so the very first thing I do is I graph my wave axis. Let's go ahead and do that down here at -4. Alright, here's my wave axis. Now let's see here. So this is at -4, amplitude of 3, so I'm going to go up 3. So, no. Okay, and then down here, 1, 2, 3, kind of like that right there. Again, amplitude is right here, same as up here, A is 3. Okay, so it has to oscillate in between there with a period of 1/2. So I'm going to change the scale of the x-axis here. So I'm going to expand it a little bit. So normally, let's figure out where we start first. For a sine wave, I would start at the origin here, but this has been shifted 1 left and 4 down. So 1 left, 4 down, I'm going to start right here. That's where I'm going to start. Question is, and that's assuming that I have a this is going to be fun to graph. I have a period of 1/2. Very, very difficult to graph this. You know what we're going to do, because it's going to be so contracted, it's going to be very, very difficult to graph. Let's change b to just pi. Okay, let's change b to pi. So I'm going to b is equal to pi here, and this is going to change. So let's cross this out and let's calculate a new period. So b now is pi. That means period's going to be 2 pi divided by pi, or period length 2. This is going to be a lot easier to graph. Okay, period length 2. And let me erase this 2 here. I'm going to change the scale just to expand it, because again, if you don't change the scale and it's so contracted here, it's kind of hard to graph. So I'm going to call this out here -1, and this 1, and this is length 2 right here. There we go. So I'm going to change the scale of my x-axis, and I can do that. I can change the scale to anything I want. Let's expand it so you can see things better here. And I changed the original function so we can graph it a lot easier. So ignore that and think of this right here. Period length is 2. Now I'm not going to start there at where I had it before. I'm going to change that location too as well, because I changed the scale, so I got to change my starting point. Okay, so let's redo this. My shift is the same. I got to go left 1, down 4. But since I changed the scale, I got to go left 1 over here and then down 4. This is my start point right here. Okay, now period length 2. So my starts here, I go over 1, over 2. That's where I'm going to end it right here. Again, every 2 units on the graph is length 1 because I changed the scale. It goes -1/2 and then -1. Over 1/2, then over 1, length 2. So this is my period. Period is equal to 2. So I changed it here. I only changed it once again just because with the period length of 1/2 on the scale right here, it'd be extremely contracted. It'd be very difficult to graph, very difficult to see. So just change it to make it a little bit easier for us. Okay, now we have an amplitude of 3, so we got to go over 1/4 of the period, and then up, then back down to the axis, and then over 1/4, and then down, and then back up. So this is going to be my sine wave here for 1 period only. Once again, I changed the scale of the x-axis to help me expand a little bit so I can see the graph a little bit better. Okay, and that's a skill that you're going to have to get used to. All right. With any instructor, whether it be me or you, in the future you're going to have a few other people. They're going to change scales and you have to adjust. And when you do your homework and practice, you're going to have to adjust too. Okay, that's a good warm up there. Let's get right into our new section 4 here, and let's talk about some new identities that can be developed. I'm going to start off with the unit circle here with radius 1. So this is radius 1 here, so it's 1, 0. I'm going to plot P right here. This is theta. P has coordinates x, y. So this is y here, and this is x. And this is the radius r, or 1. Let's just put a 1 there actually, because we're on the unit circle with radius 1, so r is 1. I'm going to put a 1 there. Okay, so we're on the unit circle radius 1. We know that sine theta is y to r, but on the unit circle, let's write this down here. On the unit circle with radius r equals 1, the sine theta, as you guys know, is y divided by 1, or the y coordinate, whereas cosine theta would be x to r, or x divided by 1, or the x coordinate. So really this is cosine theta comma sine theta, anywhere on the unit circle here. When you think cosine of what angle, think x coordinate on the unit circle, y coordinate for the sine. Okay, now with that in mind, we also have this too. We have the Pythagorean relationship here. Okay, the Pythagorean relationship is that on this little triangle in here, this little right triangle, we have x squared plus y squared equals r squared, but r is 1, and so you have x squared plus y squared equals 1 squared, which is obviously 1. Why is that? Well, because r is 1. Well, given that, what we can do is do a little substitution here. We can take these right here, what we know about y and x. Y is equal to sine theta, x is equal to cosine theta, and we can substitute them into our Pythagorean relationship and get some unique, what are called Pythagorean identities, which are basically formulas for sine theta and cosine theta. I'm going to substitute cosine theta in for x. I'm going to substitute sine theta in for y and see what happens. So here we go. In for x. In for x goes cosine theta. So I get cosine theta squared plus, and I take sine theta, substituting for y, I get sine theta squared equals 1. Now it's not typically written like that, the way this, because it's a little complicated with all the parentheses. However, you're going to see it like this. You're going to see cosine squared theta like this. These two are equivalent. Okay, you're not squaring the angle theta, you're squaring the function, which means the cosine of that angle. So keep that in mind. You're not squaring theta there, you're squaring the whole function evaluated at the angle, plus sine squared theta equals 1. This is called your Pythagorean identity, and let's highlight it. This is equation 1. Okay, EQ number 1. This is the Pythagorean identity. This has to be memorized because everything is based upon this. Okay, your first Pythagorean identity. Okay. Now, any equation that I highlight and name, go ahead and memorize it and know its different forms. Okay. So let's go down here and let's develop a few more here. Okay. First of all, if I take this equation and divide all terms, both sides, all three terms, by, let's say, cosine squared theta, I get a new identity, which is going to become our second major Pythagorean identity. Let's write that down. I want to divide, okay, equation number 1 by cosine squared theta, and I want to see what we get. Okay, I'm going to take all three of these terms and divide it by cosine squared theta. So here we go. So cosine squared theta divided by cosine squared theta, plus the second term, sine squared theta divided by cosine squared theta, is equal to 1 divided by cosine squared theta. And what we're going to do is simplify and see what we get. We know this first term right here is 1, so anything divided by itself is 1, plus this. Now, we know that sine theta over cosine theta is tangent. So, sine squared theta divided by cosine squared theta would be nothing more than tangent squared theta. And we also know that 1 over cosine theta is secant theta. So 1 over cosine squared theta would give us secant squared theta. This is your second one. This is equation number 2. Now, if we get creative, we take equation 1 and divide it by sine squared theta instead of cosine squared, we get something different. Okay, so now let's divide equation number 1 not by cosine squared theta, but by sine squared theta, and let's see what we get. Okay, write kind of small because we got to fit this on the page. So here we go. I'm going to take cosine squared theta divided by sine squared theta. Take the second term divided by sine squared theta. And take the right-hand side and divide it by sine squared theta. Now simplify. Let's see what we get. We know that cosine theta divided by sine theta is cotangent theta. So cosine squared theta divided by sine squared theta should give us cotangent squared theta plus, and then this becomes 1 is equal to, and this right here, we know that 1 over sine theta is cosecant theta. So 1 over sine squared theta should give us cosecant squared theta. This becomes Pythagorean identity number 3. Or E simply put, equation number 3. Now, what you're going to have to do is you're going to have to know the different variations of these. So what I'm going to do is I'm going to isolate cosine squared theta and see what we get. I'm going to isolate tangent squared theta and see what we get. And I'm going to isolate here cotangent squared theta and see what we get. And I want to write down the variations of these because you're going to see these throughout the homework, throughout the lesson, throughout our examples. And it's one thing knowing all 3 of these, but it's another thing knowing all the different variations and be able to know them by sight, like I do. Okay, so we're going to take each one at a time, and we're going to isolate one function at a time to get their different variations. So turn the page, and here we go. Here are the variations. And you got to know these by heart too. Let's take equation number 1. Now, equation number 1 was our first Pythagorean identity. Cosine squared theta plus sine squared theta equals 1. Now we have 2 variations of this. Okay, I can isolate cosine squared at first. So if I do, I get cosine squared theta is equal to 1 minus sine squared theta. Or if I want, I can isolate sine squared theta, and I get 1 minus the cosine squared theta. Those are 2 variations, and you're going to see these. In fact, these are difference of squares. Okay, 1 squared minus sine squared is the difference of squares. I could factor this actually and write it as 1 minus sine theta times 1 plus, oh, that's a plus sign. I'll change that. 1 plus cosine theta. Just by factoring. From here to here, you can factor. Now, the reason why we can do that, let me just put up here in red just so you can see it, is that we know that a squared minus b squared from algebra is equal to a plus b times a minus b. Okay, that's factoring the difference of squares. Difference of squares. Just an old thing that we used to know. That's what I did from here all the way to here, is I just factored it. And if you do the other one, or factor the other one, you get 1 minus cosine theta times 1 plus cosine theta. Oh, I just noticed a mistake up here. It's supposed to be sine right up here. Sorry guys, supposed to have to stay consistent here. Okay, so make that fix. Alright, now, if you take equation number 2 and work with that, you get something different. So equation number 2, you have 1 plus tangent squared theta is equal to secant squared theta. And if I isolate the tangent squared theta, I get secant squared theta minus 1. And that's a variation that you're going to see in your work. You'll see that when you get there. Alright, if you want to factor that, you can, because this is also a difference of squares. You get secant theta minus 1 times secant theta plus 1. Again, factoring as we did back in Algebra 1. Alright, factor. Let me write that down more clearly here. Okay. Now the third equation, getting close here. The third one is cotangent squared theta plus 1 is equal to cosecant squared theta. Now if you isolate the cotangent function, all you do is subtract 1. So you get cotangent squared theta is equal to cosecant squared theta minus 1. And guess what? That could be factored too. You can write it as cosecant theta minus 1 times cosecant theta plus 1 if you factor. These are all variations, which you're going to have to be able to see in your work as you step things out, as you prove things, as you simplify things. And you have to recognize that one equals the other, that this equals this, that this equals this. You can replace one with the other, all right, because they're equals. When you see cotangent squared theta, oh, there should be a theta in there, all right, it's equal to cosecant squared theta minus 1. Or if you see tangent squared theta, you know that's secant squared theta minus 1, and so on. You have to be able to see those things as you do your work. We also have the reciprocal functions. This is review. You already know these. Cosecant theta is reciprocal of sine, so it's 1 over sine theta. These are called the reciprocal functions for obvious reasons. This gives you 1 over cosine, cosine theta. And then cotangent is a reciprocal of tangent. Cotangent is reciprocal of tangent, so you get 1 over tangent theta, or you can write it as cosine theta divided by sine theta in terms of sine and cosine. Okay, those are reciprocal functions. And you now have these two important ones. These are brand new to you. Okay, we define sine of negative theta, okay, as negative sine theta. The question is, why is that? And we also define cosine of negative theta as cosine theta, and why is that? So let's take a look at that over here on the graph here. So let me just illustrate a simple example here. Let's take P. Let's consider P1 here, and let's draw a little. Let's draw the angle, and let's go down here. Let's consider P1 and P2. Okay. Now on P1, if this is x here and this is y, its coordinates are x comma y, given your theta here, and P2, there's some symmetry involved here too, by the way. So you go x to the right and y up. Now to get to P2, you got to go x to the right and y down, or the opposite of y. So its coordinates are x comma negative y, whatever that is. So if you consider the sine, and remember sine is always the y value, notice that at theta here, the sine of that, actually let me draw negative theta. Negative theta here, let me start off with negative. Negative theta is down here, it's a clockwise rotation. Okay, negative theta. From the x-axis, going clockwise. So notice here that the x-coordinates are the same. So the cosine of theta would be the x-coordinate, would be the same as the cosine of negative theta being down here, because the x values don't change, because you go right x units and then go either up or down to get to P1 to P2. So the x-coordinates are the same, so the cosine of theta should be equal to the cosine of negative theta. And that's the second identity here. But notice that the y-coordinates are opposites of one another. And the sine of theta would be y, would be equal to the opposite of sine of negative theta, because notice that it's opposite in sign down here. And that's why we have to adjust it here in the front of the sine of theta here. Sine of a negative, let's say 45 degrees, is equal to the opposite of sine of 45. You saw us do that before when we did some evaluation back in chapter 7. These two identities right here are called reduction identities. You're dealing with what are called negative angles right here. These have to be memorized, okay? From these, everything else develops. So notice what I said right here. I said knowing these two basics, and I'm talking about these right here, all right, you can determine the following, all of these. Okay, so this you have to memorize. And if you don't memorize it, well, just visualize it here. Okay, let's go ahead and develop the rest here. Well, by the way, before I do that, let me just give you a little simple case here. Let me show you something here. We know, this is just an example now. The sine of, let's say, negative 45 degrees. That's a quadrant 4 angle. We know sine's negative there, so I can rewrite it as negative sine of 45 degrees, which is our reference angle. Just reflect it up and you get your reference angle. See? That actually is true. This is saying the same thing just in general form. They just gave you a real example here, just showing you that, hey, if you take the sine of a quadrant 4 angle, which is represented as negative 45 degrees here, it's actually a negative number, so you have to have that negative there. Whereas this right here, if I said cosine of negative 45 degrees, well, even though it's quadrant 4, cosine is positive there, so it's equivalent to cosine of 45 degrees. You could verify this on the calculator too. Play with some negative quadrant 4 angles here and prove these identities over and over again just by substitution. Pick an angle in quadrant 4, substitute in, evaluate it, and check to see if it's correct. Now, knowing these two basics, what you can do is figure out, when the world tangent of negative theta is. So what you do is you just go ahead and use the basic definition. Tan of negative theta is the same thing as sine of negative theta, all right, divided by cosine of negative theta. We know tangent sine of a cosine, but evaluate at negative theta. Well, we know that sine of negative theta is negative sine theta. Cosine of negative theta is just cosine theta. This is the definition of tangent, so we get negative tangent here. Basically, all you have to remember is that any function, any of these functions that deal with sine, when you evaluate it at a negative angle here, is going to end up negative. Anything that's dealing with just cosine is going to end up positive. Like for this one right here is the same thing as 1 over sine of negative theta. But that's 1 divided by negative sine theta or negative cosecant theta. Okay, secant of negative theta is just 1 over cosine of negative theta, which is just 1 over cosine theta, which is just secant. That had nothing to do with the sine, so it's just a positive function here. And this one here, this is a cosine of negative theta divided by sine of negative theta. Okay, we know that cosine negative theta up here is just cosine theta. Sine of negative theta is equal to negative sine theta. And so you get negative cotangent theta. Any function, any of these functions that deal with sine are going to end up negative. Just remember that. Okay, this section deals with a lot of different identities. You're going to have to make some note cards here. On all of these, right here, make note cards. Okay, front. Okay, back. On all of these note cards. And even up here on all these, this front, okay, back. Make note cards for all of them. Okay, these and okay, these as well. Why? Because you're going to need to know them. If you just make note cards, make a ton of them, and then practice them 5 minutes a day, you'll get all this down. And you'll be faster than the person next to you, I can tell you that. So if you want to be fast and you want to be able to use these and you want to be able to do your homework quickly, make the note cards, memorize them, practice them on a daily basis and memorize them quickly, and your homework will be infinitely easier. And you'll take about half as long. So you're not going to be just sitting there thinking about what to do. You'll be able to see things in your mind that other people won't be able to see just because you have these memorized. Okay, now the cofunction identities. Okay, we say that cosine is the cofunction of sine. Okay, cotangent is the cofunction of tangent, and cosecant is the cofunction of secant. So we're going to deal with these cofunction identities. What is the relationship among them of the cofunctions? Okay, and we're talking about when we're dealing with complementary angles. What is the relationship between cofunctions when the angles are complementary? So when the angles, okay, are complementary, which means they sum up to 90 degrees. So complementary. Complementary means that they sum to 90 degrees. Okay, so let's evaluate this. And before we do this, let's go ahead and draw the special right triangles, I suppose. So we can view it here. We have 30, 60, 90. to 1 root 3. And then if we deal with a 45, no, it's going to look like this. 45 and 2 root 2 root 2. Okay. Sine of 60 degrees is opposite divided by hypotenuse, root 3 over 2. Cosine of 30 is adjacent divided by hypotenuse, and that's root 3 over 2. And notice that the angles here, these right here, 30 and 60, they're complementary. So the cofunctions sine and cosine here are equal if their angles are complementary. Just keep that in mind. But is that true for all the functions, all the cofunctions? Let's take a look at that. And let's do some more work here. And let me just write this down too. So that's what I'm using right now. This basics from geometry. Tangent is opposite divided by adjacent. So 30 degrees, opposite 1 divided by root 3. So you have 1 divided by root 3 here. Cotangent of 60 degrees is adjacent divided by opposite, 1 divided by root 3. Well, holy cow, they are equivalent. The two cofunctions, tangent and cotangent, are equivalent if the angles are complementary. Is that true for secant and cosecant? I don't know. Let's check it out. Secant of 30 degrees is 1 over, is the reciprocal of cosine of 30 degrees, which is root 3 to 2. Take the reciprocal, you get 2 over root 3. So you get 2 root 3 here. And the cosecant is reciprocal of sine of 60, so the sine of 60 is root 3 to 2. Take the reciprocal, you get 2 divided by root 3 again. So it looks like that when the angles are complementary, the cofunctions are equal. Okay? Now, that's one thing it's experiencing at that. Let me write it down formally. Okay? What do you notice about the cofunctions? I'm talking about sine and cosine, tangent, cotangent, and all that. What I'm saying is this: if the angles are complementary, then we have the following to be true. We say that cosine theta is equivalent or equal to sine of its complement, all right? Okay, which is found by taking 90 minus theta itself. That's how you find your complement. Okay, complement's always added 90, so if you're trying to find the complement of one angle, you take the angle given, subtract from 90 to get its complement. Now the sine of theta is equal to the cosine of its complement, 90 minus theta. Or in radians, this would be equivalent to pi halves, if you want to do it in radians. Okay, I'm not going to write out everything down in radians, but you can express these identities in radians if you like. Tangent theta is going to be equivalent to its cofunction cotangent evaluated as complement. Secant is going to be equal to cosecant of 90 minus theta. Cosecant is going to be equal to sine of, not sine, what am I saying? That's the reciprocal function. Secant and cosecant. So secant of 90 minus theta, and cotangent is going to be the equal to the tangent of its complement, 90 minus theta. There we go. Kind of got these out of order. I should have went from here to here. Okay, those are called the cofunctions. You obviously have to memorize these. All right, do some note cards immediately. In fact, you know, if you were smart, I used to do this too. And when I was in school, I used to carry a pack of note cards with me in class, and I made them during class. So by the time I got home, all I had to do was practice them. And I used to write this down on the front, and the right side. This is on the back, of course. So make your note cards in class. Just bring a stack of them. All right, make them during class as you go through this here, and then study them when you go home, 5 minutes per day, and you'll get it down. The reason why you need to know all these in your head is because when you start simplifying and proving things, you need to be able to see these cofunctions in your head. And if you don't have them memorized, you don't know what they're equal to, then you're kind of lost. And that's why your homework's going to be difficult in the beginning, because you're not going to have all these memorized, like I do. But having said that, let's go ahead and get some practice and learn how to simplify some expressions here. Okay, now we see we have secant x minus sine x times tangent x. Let me just write it down. We're going to do all the work on the right-hand side. One of the first things and the first techniques you're going to learn is to rewrite all functions in terms of sine and cosine. So let's write that down on the right. Okay, this is technique number one. I want to rewrite all functions in terms of sine and cosine. Sine and cosine. That's your first technique. So let's do that off on the right and see what happens. And we know that secant x is the same thing as 1 over cosine x. We also know that tangent x is sine over cosine. So I've got sine x here times sine x divided by cosine x. Okay, I just go ahead and replace it with what it's equal to in terms of sine and cosine. These are equal. Now I combine fractions. That's another thing that you're always going to have to do. When you condense or simplify things, you always want to combine fractions. These things are always done, always important. So first you rewrite in terms of sine and cosine. The second thing you need to do is combine fractions. They have the same denominator here, so what we do is we look at the numerator. 1 minus sine squared x. So we have 1 minus sine squared x. Sine times sine gives you sine squared, all divided by your common denominator. And now you're looking at this and you got to be thinking, hey, I see something in the numerator. I mean, turn to the person next to you and say, look at the numerator. What is that? What? It's screaming at you. 1 minus sine squared x? Who am I? What am I equal to? Well, if you go back to your Pythagorean identities and look at all their variations, and I'm talking about up here, 1 minus sine squared theta is equal to cosine squared theta. Aha! It's from our first Pythagorean relationship here. So what I can do is I can rewrite it as cosine squared theta, or excuse me, x, we have x here, divided by cosine x. So what I did is I substituted in what it's equal to. And then you simplify, one of the cosines cancels out and you just get cosine x. And that's your end result. So it's not that bad. Not that bad at all. You just got to know your identities and you'll do pretty well. Okay, part of your homework is going to be simplifying and part of it's going to be proving. We'll do a little bit of both here. On the second one here, we want to go ahead and go for it, man. We want to multiply. Okay, and we know that a plus b times a minus b, it's called the difference of squares here, is equal to a squared minus b squared using the FOIL technique. These two things are equal. This is from algebra. So when you take 1 minus sine x and multiply it by 1 plus sine x, you're going to get 1 squared minus sine squared. That's going to be equal to 1 squared minus sine squared x, which is just 1 minus sine squared x here. Or you can use FOIL. You can do it the long way. I just use my identities from Algebra 1. All right, and then you got to ask yourself, what am I? Well, we just talked about that earlier. I'm cosine squared x. And there's your simplified answer right there. It's just cosine squared x. So you got to know your Pythagorean identity here. Okay? All right, let's get some more experience. Let's simplify this. Okay, and again, we're going to rewrite in terms of sine and cosine. Okay? Rewrite in terms of sine and cosine. That's the first thing you want to do. So my tan x plus cotangent x divided by secant squared x can be equal to the following here. I'm going to get tangent x is sine x divided by cosine x. Cotangent is cosine x divided by sine x. And my secant squared x, that's just 1 over cosine squared x. Now I have to combine fractions. Okay, so secondly, okay, I've got to combine. So combine fractions. Now when I do that, let me share something with you here. When I combine the numerator here, I use an old school technique called the 3-product rule. The 3-product rule, you're going to love this. It works for adding and subtracting fractions here. And a divided by b plus c divided by d is equal to AD plus BC divided by BD. Okay, so AD plus BC divided by BD. Where's BD there? I call it the 3-product rule because you multiply 3 times. Starting with the first cross product here, I start here, A times D, then B times C, and then of course the last one here would be B times D. You multiply the denominators. Let me just show you how it works. If I added 2/3 plus, let's say, 1/5, I start here. 2 times 5 is 10, plus 3 times 1 is 3, divided by 15, you get 13/15. Okay, first product here, second product here, third product here. It's called a 3-product rule. So again, step 1, step 2, step 3. Multiply, multiply, multiply. And it works for all fractions. It's called the 3-product rule. And what I'm going to do is I'm going to use that up here. Okay, the first thing I'm going to do is I'm going to go step 1 here, and step 2 here, and then step 3 down here. Sine times sine gives you sine squared x. Cosine times cosine gives you cosine squared x. And then cosine times sine, well, that just gives you cosine times sine. Can't really do anything there. Just multiply them together and write it out. So cosine x times the sine of x. And make sure, guys, you're putting in your variables. I see a lot of people leave out the x, and if you do, I'm going to mark it all wrong when I look at your work. So don't do that. Put in your variables. Okay, and divide that by 1 divided by cosine squared x. The denominator hasn't changed. Okay, and now we're sitting here and we go, okay, we've got a complicated fraction here. So what we're going to do is we're going to go back to grade school and we're going to multiply by the reciprocal. So I'm going to take this top fraction here, which is sine squared x plus cosine squared x divided by my denominator here, cosine x times sine x, and I'm going to multiply by the reciprocal, which is just cosine squared x. Okay, right there, all I did was I multiplied by the reciprocal, and we're going to do that all day long, all the time in this class. Believe it or not, grade school math comes up all the time. Okay, the reciprocal right there. Now, this is something special right here. Turn the person next to you and say, hey, who am I? What is sine squared x plus cosine squared x? Tell the person next to you what that is. Okay, you should have said 1. Okay, so that right there is nothing more than 1. That's 1. So I get 1 divided by something. All right. Now this cosine x cancels out with one of these, leaving just the cosine x in the numerator. So I get, actually let's wait to, what do I get? I get cosine x here divided by sine x, because that one cancels out. So my end result is cosine x, because I have 1 remaining in the numerator, divided by sine x. And then you ask, oh, who am I? Well, I'm cotangent x. My friends, that's a whole lot simpler than the beginning. Okay? So you're going to have to really learn how to use your identities here to your advantage. The second thing what you're going to have to do is learn how to prove things. And this is, some people think this is easier because you actually know what your end result's going to be. You're going to start off with the left-hand side and you're going to try to prove that it's equal to the right-hand side. Start with a complicated expression here and simplify it to get the right-hand side. So once again, you start with the left-hand side, the complicated one, and you show through equality here that it's equal to whatever you see on the right. And the right's small because we've got to fit it all in here. So I'm going to start off with the cotangent theta minus tan theta divided by sine theta times cosine, fix that, okay, no t there, fix, just cosine theta. Now this is going to be equal to something, and I'm going to show that it's equal to my end result down here, cosecant squared theta minus secant squared theta. That's my goal. Okay, I'm going to show it through equality here. I'm going to show that the first is equal to the last through a bunch of steps. Don't know how I'm going to do it, but I'm going to go for it. Okay. the very first thing what we could do is re-express all these functions in the numerator in terms of cosine and sine. So here we go. So cotangent theta is cosine theta divided by sine theta minus tangent, which is sine theta divided by cosine theta, all divided by the denominator, which doesn't change. Now I combine fractions, okay? The three product rule again. Or you can use equivalent fractions. You could multiply the first fraction by cosine over cosine and the second one by sine over sine and do it equivalent fractions like you did in grade school, either one. Or you can just do this quickly here. Step 1, step 2, step 3. Okay, so here we go. Cosine times cosine is cosine squared theta minus sine squared theta, all divided by the product of the two denominators, which is sine theta times cosine theta, all divided by the denominator, sine theta times cosine theta. Now this cosine squared theta minus sine squared theta is not equal to 1 because it's not a plus sign here. So let's go ahead and multiply by the reciprocal, see what we get. So we could take this top fraction here, cosine squared theta minus sine squared theta divided by this denominator, sine times cosine theta, multiply by the reciprocal of this, which is 1 over itself. And notice something here. Let's see here. Let's just go ahead and multiply the fractions. Let's multiply the numerators. We get cosine squared theta minus sine squared theta, all divided by this times this. So sine times sine gives you sine squared theta times cosine squared theta. And you got to be looking, how do you get from here down to here? That's a good question. So what's that middle step that's going to get us here? So what we're going to do is we're going to split the fraction. And this is the difference of two terms. So when you have a single term and you want to get to two terms, just go ahead and split the fraction right here. This is another technique I use sometimes. So split the fraction into its parts. So I'm taking the first term divided by the denominator minus the second term divided by the denominator and simplify it, and you'll see that you get your result. So what do we get? Let's put this in blue. So this is a key step here. So you get cosine squared theta divided by the denominator, sine squared theta, cosine squared theta, minus sine squared theta divided by the denominator, which is sine squared theta times cosine squared theta. And if you see closely and look closely here for a while, these terms cancel, these terms cancel. The 1 over sine squared theta is the cosecant squared theta, and the 1 over cosine squared theta is the secant squared theta, and I'm done. And when you're really good, you'll put down QED at the end. That's Latin. Okay, it's a Latin term, and it's something that you can even Google this right here, QED, and you'll notice that it means quad eris demonstratum. Demonstratum. It's Latin for that which was to be demonstrated. That's what it means. That which was to be demonstrated. Demonstrated. I was supposed to demonstrate to you that the left is equal to the right, that this first expression is equal to the second expression, okay? And I did that. The first is equal to the second step, okay? The first is equal to the second, which is equal to the third, which is equal to the fourth, which equals to the fifth, which equals to the sixth, which equals to the seventh, all right? If they're all equal, then by transitivity, the first is equal to the last. Okay, and the Greeks back 600 years before Christ, back in the Pythagorean days when they wrote their mathematics, used to put down QED at the end of their proofs. And QED, like I said, is quad eris demonstratum. Quad eris demonstratum, QED, that which was to be demonstrated. And so if you actually, figure out a proof here, go ahead and put that on the end. Be confident. Tell me that you got it right. Show through equality right there. Okay, let's do a few more. Let's gain some more experience here. Let's take the cotangent of A. Again, we can switch variables here when we want. Times, 1 plus the tangent squared of A, where A is the angle now, divided by tangent A, and let's show through equality that you get just cosecant squared A. So let's put down our goal down here, cosecant squared A. I always put down the goal at the bottom because it gives us a sight where we're supposed to be headed here, guys. And that's where we're going to go. We got to get to that. Take the complicated expression, simplify it, and get the less complicated expression. The very first thing what I'm going to do is I notice that I have an identity in here. This right here, this 1 plus tangent squared A, is an identity. Turn to the person next to you, tell them what it's equal to. Alright? Now if you look back in your identity, so up in the very beginning of the lesson here, let me see, where is it? It is, oh, it's right here. It's equal to secant squared of that angle. Okay, so let's go for it and let's use that. That's why it's nice to have these things memorized, is because when you see 1 plus tangent squared A, you'll know it's equal to secant squared A, and you can substitute that in. So I can say, hey, I got cotangent A times, not this, but what it's equal to, all right, and it's secant squared A, all divided by, tangent A. That's your first step. So this became this right here. Now the second thing you could do is, go back to sine and cosine and rewrite this expression in terms of the sine and cosine. So let's do that. So cotangent is cosine A divided by sine A. Secant squared A is just 1 over cosine squared A. Tangent is sine A divided by cosine A. You got to know your definitions really well to be good at this. Then you want to simplify a little bit, and you also want to multiply by the reciprocal. So what do I have? Let me see. I can simplify up top a little bit here. This cosine A is going to cancel out with one of these, leaving just cosine A down here. And then what I have is 1 in the numerator, so 1 divided by sine A times cosine A. So sine A times cosine A times the reciprocal of this, which is cosine A divided by sine A. So I multiply by the reciprocal again, multiply by the reciprocal. Okay, now at this point you want to do a little more simplifying. I see that cosine A divided by cosine A is 1. I get 1 divided by sine A times sine A, which is sine squared A. Notice that I put in my steps, and that's equal to cosecant squared A. Alright, and then I'm done. I met my goal. Quad eris demonstratum, QED. Now I put the equal signs in, I show my simplifying, I show my steps. First equals second, which equals the third, which equals fourth, which equals the fifth, which equals the sixth. So my first must be equal to the last by transitivity. Alright, and I met my goal. You always have to start off with the more complicated left side and show it's equal to the right. Alright, last one. Okay, on this one here, I'm going to start off with secant x minus cosecant x divided by secant x times cosecant x, and I'm going to show it's equal to sine x down here minus cosine x. That's my goal. Okay, so the first thing I do is I rewrite in terms of cosine and sine. So 1 divided by cosine x minus this cosecant, which is 1 over sine x, all divided by 1 over cosine x times 1 over sine x. Notice I'm using the same technique over and over again. Then I combine fractions again. I'm going to use my 3 product rule. So I'm going to multiply, that's my step 1, multiply step 2, multiply my step 3. 3 product rule, that's probably the fastest way you can do it in your head. So sine x times 1 is sine x, minus cosine x times 1, all divided by cosine times sine, all divided by this product here, which is 1 over cosine times sine. So 1 over cosine x times sine x. Now I get this complicated fraction which needs to be simplified, so I always multiply by the reciprocal. And you got to show that. So you start off with this top fraction here. You go sine x minus cosine x, all divided by cosine times sine, times the reciprocal again, which is cosine x times sine x. The reciprocal of this fraction here is just cosine x times sine x divided by 1. Again, multiply by the reciprocal, multiply by the reciprocal again. So from here to here, multiply by the reciprocal. And then show you're simplifying. Cosine x times sine x divides out, and you get your end goal. Cosine x minus cosine x divided by 1 is itself. Alright? And this is a good taste of your homework here in 8.4 here. You're going to have to do this. You're going to have to check your solutions online. Alright? Make yourself proud. Do your homework. And the only way to get good at simplifying and improving is by pure practice. And make sure that you get help immediately if you get stuck, which you will. So I will see you in class tomorrow. Work well with each other. And also check your work online. Make sure you do that. Some of you guys aren't, and you better, because if you can't do it in your homework, then forget any quiz or test. I can tell you that. So be honest, do good work, and check your work and get help when you need it ASAP. I'll see you tomorrow.